And now we will move to the ForeSee results regarding the standardization. By first presenting you the methodology that we use to achieve the results that I'm going to show you next. So in parallel, in each project, we perform the market evaluation and identification of the most relevant standards in each project. We perform an assessment of the technical partners' contributions as the standardization task leaders involve their respective partners in the projects to evaluate the standards. We perform a reassessment and the validation according to the progress of the systems that are being developed in the projects. We perform also an evaluation on the importance of the standards. We build the radar charts for the representation of the level of adoption for the standards, which will present a common vision. So it will be an aggregation of results from each project later. And the collaboration to represent then a common vision for the ForeSee cluster on the standardization following with these best practices. So the tool that we use to demonstrate the standardization evaluation is the radar chart. So as you know, the standards are tools to be chosen in context to support the given ecosystem and its digital transition. And to support this representation, we use in parallel the creation and re-evaluation of this chart that you're seeing. So the radar chart is a graphical representation of the most relevant standards on the global radar screen, which are tied to a description of each standard on the separated table. So the radar chart provides a simple view on the standardization assessment, illustrating technology of all the elements that may be of relevance for the project developments. This chart, as you can see, is divided into 4 quadrants, showing the ForeSee strategy for delivery of the candidate standards, adoption, monitoring, or participation in development, or in ecosystem development of standards. So in each standard of the radar chart is used to provide visibility of the status and maturity of a standard or initiative. Each standard or initiative are first identified and further continuously updated to track progress, and the standard of initiative evolves. As you can see, the 3 levels here on adopted, candidate, and tracked, which adopted on the center, which means the standards that are being currently adopted in the projects. Moving on to the first example. So as we perform this analysis in 2 separated examples, the first one, as you can see, is the data-related standards. And we performed here for the ForeSee projects, the data-related standards, the ones that are more important to be highlighted. In here, they are classified according to their category, which you can see on the table on the right side at the bottom of the page. So we have transverse, domain, and technological standards, and these are the mapping that you can then analyze with more detail. We also then providing you the list of the standards and the respective references for each of them, and the action and the current action from each standard. And here for the second example, I'm showing you the radar chart for the predictive maintenance related standards. Where in specific we analyze the standards that are particularly applied in the predictive maintenance, this chart is populated because we wanted to bring your attention to these standards and support their adoption in the future IoT. In parallel, we also present you here then the references for each standards. And now we can move to the application in the use cases. In here, it's a section where we would like to share with you some best practices that are being applied in each of the projects, following the application in the ForeSee projects. So we will start with programs.
Okay. You can hear me, Marco?
Yes, perfect.
Okay, I'm Angelo Merlo from CESI, partner inside the programs project. I'm going to show a couple of examples of application of standard for our use cases. One is related to the standard EN 15341, that is KPI for maintenance. The scope has been to apply such a standard to one of the modules that we develop in the project, that is called maintenance schedule optimization module. This is a sort of decision-making module that select the optimal, the most cost-effective strategy of maintenance among corrective, preventive, and predictive. You know, predictive is good practice, of course, but sometimes it's not the more cost-effective one. Sometimes happen that preventive one based on scheduling, time scheduling, or corrective one to wait till the failure could be maybe cost-effective because there are no collateral damages. So to select such a strategy, the optimal one, we develop a life cycle cost model that include all the maintenance related costs, because costs are the cost driver for the management of companies. So to decide which is the best, of course, cost is one of the essential, the key parameters. So minimizing such a cost, we can find the optimal strategy among the three I mentioned before. To develop such a cost modeling, we introduce several KPIs related to maintenance tasks. And then we use some of the KPIs inside such a standard in order to have a common view, a common understanding of what we are introducing in the formulas. Once we have built such a formula, our decision-making tools implemented, and we apply for the robot welding use cases to produce solar panels, and for machining workshop where they produce dies and molds by milling operations. So we apply that, and the tool works and has bring benefit to the partner in terms of optimal selection of the maintenance strategies. Okay, so you can move to the second one. Okay, this is an application of PMML, that is Predictive Model Markup Language Standard. This is not an EN or ISO standard, it's a de facto standard developed by the data mining group. This is a language that allows to share algorithms between machine learning applications. So it's very useful if we want to introduce a modular approach. For example, in our cases, we divided our predictive maintenance platform in two basic modules. You can see on the right figures the learner block in red. That is the module that parse a lot of data coming from the field. This is a module that should run on high performance PC on the cloud or on server, on premises server, because that to parse and evaluate a lot of, let's say, sorry, a huge amount of data in terms of gigabyte of terabyte. So have to run in high performance PC, definitely. Here, such a module will develop or will generate the algorithms for prediction. Such an algorithms will be then shared, update once per week, so one per month, and sent to the predictor block that run locally on CNC of the machine or in a local PC close to the facilities. In this way, such a predictor block just gets, using PMML language, get the algorithms that will be generated on weekly, as I said, on weekly or a monthly basis by the learner block. They use such algorithms that are not very huge as a file and make a prediction, reading a streaming file from the workshop. For example, once a day you have predict the state or residual useful life of the machine, but in this way you just parse some megabyte or kilobyte of file, because all the let's say all the huge operations are done on the cloud that periodically send the algorithms to the module, the predictor module on the shop floor. In this way, we can have the possibility to use a modular approach, to use a fog computing approach, so very close to the machine or where data are generated, and we apply to as well to the machining workshop and to the robot welding systems, as I said before. And the benefit was huge because the module can run, as I said, on a CNC or a local PC, and with not very high consuming of resources, while we keep in the cloud on premises the heavy part that, as I said, just send to PMML the algorithms to the predictor module. So that's in synthesis what we done in programs with such standards. Okay, Marco, I finish.
Thank you very much, Angelo Merlo. We'll now proceed with Serena project with Dr. Cosmas Alexopoulos.
Hello, also from my side. In the Serena project, we will discuss on the use of the Mimosa Standard. So the Mimosa Standard provides an information exchange model that allows the description of assets that are there in the manufacturing floor. It provides capability of registering assets in the database and then to manage information related to condition monitoring, to maintenance, reliability information. And so it provides, in short, a kind of a meta model or a data model that we have used for our system. We have applied the Mimosa Standard, as you can see on the figure on the right-hand side, in the backend system of the Serena solution, in which the information from the assets is being stored. And this and the use of this standard has allowed us to deploy and utilize the solution of the project to several use cases. So it's the same model applied in many cases. In this case that we are presenting here, the solution has been tested in the case of our partner, of our industrial partner VDL. It's a company that produces metal parts, and more specifically, the predictive maintenance issue that we had in this case was in the rolling form machine, in which we wanted to be able to predict when the coating in the rolling mills becomes corrupted or is not in a good condition in order to produce the parts in a proper quality. And for that, we have, of course, used sensors to measure information such as temperature or pressure that is being applied in the machine. All this information is then transferred to our Serena cloud infrastructure. And in the cloud infrastructure, we have used the Mimosa metadata to describe our data. This schema, more or less, is also applied in our other cases, as I explained initially. In technological terms, we have used JSON format, and then we somehow developed a JSON wrapper around the Mimosa standard in order to help us manage the information. And Mimosa also helped us with the automatic generation of IDs that we have used also in our project, I mean, in the Serena project, and we have used them as Serena IDs. And this helped us accelerating the whole process of registering equipment and assets from the shop floor. And of course, another objective and another benefit, let me say, by using this technology is interoperability, because this is a standard that is available, and other systems, other organizations can also utilize it, and this allows and can help us in addressing interoperability issues. So thank you for your time.
Thank you very much. We will now proceed with the deep break example. And this is an example on the predictive predictive analysis on the blade machine used on the Philips use case, which is firstly represented on the figure on the left. The machine production is often interrupted because the shaving cutter cold forming press stops. The press has fixed dies which operate cutting or bending process. These processes are monitored by acoustic emission sensors. Two critical failures modes within dies are the punch breakage and the fatigue. Based on the number of punches per second, the acoustic emission and quality data predictive monitoring assesses if the usage cycle is as expected and to detect wear. So we will now present on the figure on the right-hand side the representation of the Philips network and how the standard, the protocol for the NGSI will become a benefit in this daybreak project. So the files, the transmission of the data in MQTT provides all the data by topic. The interface enables in runtime get all data from MQTT and save all data in each file, including the acoustic emissions, which is a passive method that monitors the transient stress waves generated by the rapid release of energy from located sources, such as a fracture within a material. Then the exchange of information occurs as IDS connector to get and convert in NGSI format. All the data subjected to be monitored to be sent to Orion context broker. Likely, after all data entities can be consumed by the existing consumers. So the objective is to assess through alerts if the usage cycle is as expected. The acoustic emissions determine whether there is wear or there are anomalies through the machine learning. To better explain to you how what are the benefits of this usage, we will first explain how we standardize the data structure. So in this example, in the ZBreak project, the NGSI format is used for any type of software, a large amount of information to make available to customers. The use of this standard facilitates customers as consumers, as many of them do not have the technical knowledge or are not prepared to consume the information as it is collected. Thus, ZBreak is in particular in the use case of Philips, allows always to be made available in the same formats and can be consumed through any type of software. As indicators, the client-side software must specify which field the customer demands to access the information, and the system is available in the default data structure. The client then can access the desirable results through a mobile or web application of fireware. So the main benefits for the GNSI can offer can be divided in set of business benefits for ZBreak to their consumers. So first, the platform is widely used. ZBreak benefits from being fed by a large number of customers. Secondly, the data analysis process is easier, as ZBreak customers and technical providers will request the data in the same format. The format of acoustic emissions and the state of the machine, for example, is always the same. Also, the data structure can be easily replicable through different customers. ZBreak does not have to make a new structure for each customer. It can be replicable for new customers. And finally, the platform is prepared for bespoke developments, as the customer can filter what wants to receive from their machinery. If necessary, the data structure can also receive new fields and be shared with customers in need. So to conclude, NGSI was selected upon cost-benefit analysis, as many of other standards could be suitable candidates. The application of this norm enables ZBreak to become more efficient, reducing failures within predictive maintenance. Standardization is, as demonstrated in this example, when GSI a key factor for Industry 4.0. And now we'll proceed with ForeSee project with Giovanni Orio, please.
Yes, good afternoon. My name is Giovanni Diorio. I'm going to present how within the ForeSee project, how we use it, the asset administration shell concept from the reference architectural model for Industry 4.0. So I will describe a little bit the challenge. First of all, during the ForeSee project, we developed a middleware infrastructure that to enable data integration from distinct industrial physical assets. And also, in order to provide data to external application, to provide data to analytics services for predictive maintenance solutions. So one of the challenge was, it was also one of the requirements for the infrastructure was the presence of a well-defined mechanisms to enable external systems to gain access to the ForeSee, to the infrastructure data. So, taking into account this challenge, we decided within ForeSee to implement a component that is the ForeSee Asset Administration Shell component, and this component is actually an implementation of the RAMI 4.0 Asset Administration Shell. Actually, this component delivers a machine-readable technology and device-agnostic description for a physical asset, and provides all the necessary mechanisms to allow an external application to get access to the data that are part of the middleware infrastructure. So actually, the administration shell exposes the ForeSee data to the outside of the ForeSee ecosystem. The exposed data are organized have a particular structure and are organized within, are described within the manifest. The manifest actually is a meta model that describe the capabilities of the physical assets according to the specification of the RAMI 4.0. So actually, during the execution of the ProForesee project, we demonstrated the asset administration shell as we can see in the figure on the left side, where basically the asset administration shell has been deployed between an external application and the ProForesee middleware infrastructure. And the rule of the asset administration shell in this case is to stream data to an external application. In this case, the application that we had is a third-party application that is named Share Platform, and uses basically this application uses ProForesee data to create augmented reality services. So the benefits of this approach actually are, we can summarize the benefits in three points. The first one is that the asset administration shell actually provides a standardized manufacturer independent digital representation of a physical asset. The second advantage is that actually it establishes the foundation for interoperability between applications managing the industrial systems. And finally, we can see that by using the asset administration shell, our system, in this case, the ProForesee solution, can be easily expanded and can be easily improved by any external application. Actually, we can connect and disconnect external applications because we have defined a standardizing interface that allow any application to easily access ProForesee data and provide, create services on this by using this data. So this is what we have done, and this is also the contribution for the standardization within ProForesee projects actually.
Thank you very much, Giovanni Orio. So we'll now proceed the pre-com project with Elena Urquia.
Yes, hello. Well, I'm going to share with you the Umati Standard initiative, which was very interesting for us and we discovered during the pre-com project. What I have to say first is that the pre-com project has 3 use cases. In each of these use cases, we have the equipment manufacturer and the final client of this manufacturer. And then over these equipments, we make the connection of the systems to gather, well, we put sensors and we make the collection of lots of data to gather information for predictive maintenance. So what we find here is that normally a customer has many different machines that have to be connected to different systems, whether to gathering data, whether to make to connect to other applications, and in this area it's very important for us to find interoperability and connectivity standards that make it easier for us and for the final users also to make all this connectivity. So during the project, we knew about the Umati Standard, which is an initiative jointly supported by VDW and VDMA, which are the German associations for machine tool and capital goods. And they were in this initiative making this standard to make this connectivity easy. So as we can see in the graph in the right side, normally when we have a machine tool, we have different data sources like CNC, PLC, HMI, different elements of the machine, which have native protocols and interfaces. Over that, normally the machine tool manufacturer constructs all his data structure. And so we have then the data which can be controller specific and also machine tool manufacturer specific data. So what we do with Umati is we have a layer of a transformation gene. This works over the OPC UA protocol, which is being more and more adopted in the market. And over this layer, we have a common semantic which makes it very easy for anyone who has then built an OPC client to know what data they are gathering and to connect very easily. Also this standard was not used from the beginning. We made some testing with some of the partners, and we find this initiative very interesting because it's, as I said, a very easy connectivity to a variety of machines and suppliers. And this can be connected on the lower side. It's very standard to connect machine to machine, machine to component, and then also connect these different machines to softwares that can be in the final user shop floor. So it opens a lot of opportunities, and it's also easy to implement. And we are still looking at it and seeing how it's accepted on the market, and see if it's very widely used. And that's what I wanted to say. Thank you for the slot.
Thank you very much, Elena Urquia. And now for the final use case, we have from the Uptime project, Dr. Ives Caron.
Yes, thank you, Marco. Good afternoon, everybody. Yes, on the Uptime project, as you can see on the right part, we have a set of components we have brought together to make a predictive maintenance platform. And I will insist here on two types of standards. Here's the first one, AMQP and MQTT. It's technical standards, and these standards are used to exchange messages between the components of the platforms and to facilitate exchange with potential also external components. And of course, exchange of message is very important in these cyber-physical systems. And with MQP and MQTT, we did not find limitations corresponding to the needs and the requirements we have in exchanging data messages between the different components, from sense to detect to predict and decide. And so the benefits are especially because beyond the interoperability of the components of the platform is the possibility to integrate also these components with other components, of course, using also the same standards for to exchange messages. And so you can extend the capability of the platform, integrate it to the context of the customers, and use also additional microservices to improve the capabilities of each of the components. Next slide, please. On the other side, I would say we use also the ISO 13374 standard, which is a functional specification. Before, I think it was presented the Mimosa CBM standard, which is a schema, a data model, as it was said before, which is cited in the ISO standard. What is interesting, it is a functional specification defining the different functional blocks, and which is fully followed by the Uptime functional architecture, and the implementation schema from Mimosa supports the exchange of data between these different functional blocks. So thus, the Uptime platform compliant with this ISO standard with large application. So it's possible to have the basic features we wanted to achieve with Uptime platform: modularity and scalability. And the Mimosa OSA CBM technical specification is maintained, available in new formats like JSON, as said also before. And so the end users will save cost and benefit of the solutions where when he needs new functionalities to exchange things or extend them, it will be facilitated at marginal cost, hopefully. So next slide, please. Yes, I will give some words about the lessons learned and perspectives. We proceed, as this was described before, listing all the relevant standards from different types. And when we want to make predictive maintenance, we have a large scope of data, and also we have different maintenance standards to take into account, maintenance data standards, and also more technical standards. So we have a lot of standards, and also new standards in the making. So it's a little bit overlapping and sometimes not so easy. But the aim is not to know all the standards, but to know that they exist and use them for a specific use case. So we also explore the ontologies, which are which define formally the concepts and the relationships, and which with ontology it's possible to express formally knowledge and to exchange also messages of high semantics between different components, allowing them to interpret these data exchanges through references as ontologies. But on the other hand, ontologies need maybe more maturity. It's a long way to have a good ontology, or to reuse also ontologies. And by the way, probably it will not cover all the requirements we can have in industry. For instance, to combine also requirements, models, and so on. But it will be clearly helpful for specific aspects. So Uptime, we map also with the concept of the reference architecture of RAMI 4.0. And I think the detailed specification for the asset administration shell will be very helpful, but needs more investigation. It will be helpful, for instance, to integrate a lot of data concerning equipment for different use cases, different processes. But after the providers of this equipment need also to be more mature to comply with this specification. So considering the complexity of the landscape of standards, I think we need maybe a common framework of standardization, and also external reference data libraries interpretable by machines, especially for component properties. Concerning, for instance, maintenance, it will be very helpful to have standardized mecha models, for instance, for pumps or for compressors or things like that, and be able to adapt them to their context of use, and to be able, yes, to follow the properties and the event happening in a production system, and to implement these predictive maintenance strategies. I think Antoine will make a more complete description of the landscape concerning maintenance standards. One important thing also is to collaborate with people from maintenance disciplines to make the link with and to take benefit of the new technologies and the standards more focused on data processing. So, but I think we can at the same time have a common and simplified framework to use the existing standards and first the maintenance standards, which are quite stable and where we can add extensions as needed for new concepts and new concepts. Thank you.
Thank you very much, Dr. Alex. And now we will proceed with the key speaker, Antoine Despojols from AFIM. He will show us which standardization